My name is Yusuf Mehta. I'm a professor in the Department of Civil Engineering and director of Creates. Anybody who's online, can you please step up and introduce yourself really quick?
Hello, Professor Yusuf. This is Dr. Abhinay Kumar, PhD from IIT Guwahati, and I'm working as assistant professor in Thapar University in Patiala, Punjab. I have been a big fan of your work, especially your work that you have done in pavement engineering education, because I'm very much interested in engineering education, and it will be really a pleasure and honor for me to attend your course. Thank you.
Anybody else want to just step? Yeah.
Myself, Ujjwal Solanki, working as an associate professor in Department of Civil Engineering at Darshan University, Rajkot, Gujarat. Sir, I have a number of times referred your paper, Yusuf Mehta, Yusuf Mehta, Yusuf Mehta. So I am highly interested to learn from you. So it is my chance to learn from you, sir. Thank you very much, sir.
Great. Thank you. Anybody else?
Sir, I am Junarani Uja and joining as assistant professor in BSST Burla, Odisha. Now I am pursuing PhD at IIT BHU, Banaras.
Welcome. Yeah. Anybody else? Please speak up.
Hello, good afternoon, sir. My name is Dr. Nasal Kumar, and I'm currently working as an assistant professor at Shulini University, Solan in Himachal Pradesh, India itself. And although I'm not from this specific field, I'm from water resources engineering and civil engineering. But a couple of my PhD students are working on pavement design, pavement material, and construction materials. So I was very much interested in exploring this domain of civil engineering that I've studied about 10 years ago. So, and given this GYAN initiative by NIT Uttarakhand, I thought I've been introduced to this topic from a global renowned researcher. So that was all. Thank you, sir. Thank you very much.
Yeah. Thank you for joining. Anybody else? Or anybody else there? That there are around 30 people.
Okay, so what I want to do in this course, this is for in person as well as online, is that I want you to not feel shy about interrupting me. I know I want it to be it's going to be hard, it's going to be a challenge, but I am more focused on making sure that I can explain the process of characterization, pavement design, rather than the breadth of the content. So I really want to focus on this entire session being very interactive. Otherwise, it will become a long 4-5 days, right? So I want to make sure that you guys interact with me. You guys stop me at different times, and that will make it very engaging, very meaningful, because the responses I give to your questions, people will learn a lot more than what I will do with a general.
Very engaging, very meaningful, because the responses I give to your questions, people will learn a lot more than what I will do with a general, just by going through the slides. The slides is just a guideline. And after the slides, I think we have a tutorial where I have some open-ended questions and we can have a discussion on how to solve them. And then we can go from there. Any questions about the format or anything you would like me to change as we go through that, please speak up. It is our course, it is your course, and let's make it fun and engaging. Any questions? Okay, I'm going to go. I'm going to proceed from here, and I've got a few slides. I'm going to go through the objectives. Lecture 1. I'm not going to go through all of these, but in detail in terms of every point. But I want to make sure you can see the screen. And one of the big things I'm going to go through is how we can include sustainable materials in payments. And I'll touch on that. Why do we need a payment? How do we design the payment right? And so on and so forth. Okay, and then I will go into different material characterization, different types of design,
which is listed here: empirical, mechanistic empirical, and mechanistic design, and then a little more complications about different ways of conceptual modeling and so on and so forth. Okay. So with that, I'm going to move through this, and I'm going to go to the fundamentals of pavement design. I'm going to do some pavement ME hands-on examples, flexible pavement design, and rigid pavement design, both PCA and ASH. So that's going to come overall. So just a very brief history, and I wanted to do this, but before I go into the history, does anybody know, anybody in the audience or anybody online, why do we need a pavement? Why do we need a pavement to begin with? It may seem too basic, but I want to get this discussion started. Why do we need a pavement to begin with? Anybody can speak up? I'm muted with video. Why do we need a pavement? Anybody online want to speak up?
So for smooth movement of traffic, smooth, safe, and fast movement of traffic.
Yeah, so the big thing is for a smooth road, that is one thing, for a smooth road. So why this is important is if you're not a taxpayer, you're not a payments engineer, only a taxpayer, all you care about is a smooth road, right? I want the smooth road to go from A to B. How you do it doesn't matter, right? I can do whatever I want to do. I want a smooth road to get A to B. That's number one. Second one, you said about traffic. There's something more than traffic. Like if I have a brand new soil, does that make a need for a pavement? Why do I need a pavement? Anybody? Anybody online? Anybody here? Why do I need a pavement? I want to expand this roadway. I have a soil, right? It is there. Why do I need to build a pavement? Pavement costs money, right? Why do I need it? Anybody?
To reduce the stresses transferring to separate.
Can you repeat that again?
To reduce the stresses on separate soil.
Yes, so you are trying to protect the natural soil. That is the basic goal. So the whole idea is that the natural soil should be protected. So the reason you need a pavement is all you are doing is trying to protect the natural soil. So you're right, reduce the stresses and to make sure that the natural soil is protected. Now comes the second problem, which is the biggest issue here is that pavement design is not a very difficult technical problem. People think it's a very technical problem. It's a cost optimization problem. Okay, so that is what you need to do is, if I know that I want to protect the natural soil, if I put steel slabs in there, right, I have solved the problem. I've got a smooth ride, I put steel slab, the only difference is government can't afford it, right? That's why this entire field exists, because I know how to reduce the stresses in the soil. I can select a very strong material on the top and solve the problem, right? The issue is that I'm not dealing with 10 foot, I'm dealing with kilometers of roadway. And that is very expensive to do. And that is why I need to do. So I always tell my students that the entire pavement material is a cost optimization problem, which makes it challenging because I have to get material that's readily available and can give you the benefit of protecting the natural soil. So with that framework in mind, I'm going to thread the entire course and explain how we protect the natural soil in different ways, how we give a smooth ride, and how we can do this cost optimization process. And please, at any point, just speak up, interrupt me, not a problem. That's much better than just hearing myself, right? So, right, it's just a really brief history of pavement design. Egypt was around 3000 BC, Babylon around 2000, and then the first thing was England was macadam. That's the word macadam came about. That was the first bituminous. Bituminous is a British word as well, right? And then you have asphalt, tar, and all those words. So you have broken stone. That was the first thing. And look at this. Use of broken stones as a support structure is what is needed, right? You can just use the broken stones. And there, if you had horse carriage, that did the work, right? You had horse carriages at that time and so on and so forth. And that was just fun. Okay. Then finally, we had the first one was the American Turnpike in Virginia. And also there was one right at Pennsylvania Avenue, which was right outside the White House. That was one of the first bituminous roads in this. Yeah, right here. So right here, this is very important. Right here, this is an important lesson here. You're going from left to right, 200 AD on the left, all the way to 1900s. You can see the thickness drop. Why did the thickness drop? Can anybody tell me why did the thickness drop overall? Right, in 200 AD, it is just given in terms of proportion, right? There are no numbers there. So it dropped to 1/3, right? From 280 to 1900. So probably 1700 years, the thickness drastically dropped to 1/3. Why? Why did the thickness drop? Anybody guess?
Because the earlier designs were too conservative.
They were too conservative. That's correct. Also, they did not understand the property very well, right? They did not know what was in the property. Testing materials was very expensive, right? The hydraulic mechanical testing was not as advanced, right? So what they did was, okay, I want to protect the natural soil, make the material as thick and put the horse carriage or whatever you're driving at that time far away from the soil, right? And that's what they did. So as we moved from left to right, people started to understand, oh, asphalt has some binding properties. Cement has some load carrying capacity. Now I don't need to make it as thick, correct? And that is what that led to the early 1900s is what led to the reduction in thickness, right? I have to get used to this a little bit. So right here, that's again history of pavement design. First road, natural earth, timber, and cobblestones. You can see there are some concrete pavements. And then right here in Federal Highway, you're looking at 60. That's when they started to do looking at accelerated pavement testing facilities where they had vehicles going circles. And that's so you are seeing first roads built in concrete pavements in 1893, much later. And that's the one I told you, asphalt PA Avenue was just outside the White House. That was in 1867. And then other roads were built in 1944, 48, 50, 56. And that was when the Dwight Eisenhower signed the Federal Highway Act, where he wanted interstates to be built in entire US. And they made it very thick. All right, before I go to this slide, can anybody, I'm going to digress a little bit so I can make it a little more engaging. I hate to follow slides. How was Superpave formed? Anybody understand what Superpave? Superior pavement, superior performing pavements. It's the design methodology for asphalt pavements. Can anybody guess why that was developed? Everybody knows about Superpave, right? It was the next generation of Marshall mixed design, and it uses binder testing, mix testing. Anybody guesses on the online or here? Anybody want to take why was Superpave developed in 1990s?
So because at that time the existing way of classifying the binders, the making,
Yes.
was not able to relate to the performance. There was a lot of wrapping stresses and cracking also.
Right. So a couple of things happened.
Not able to play.
Correct. So a couple of things happened. When the Federal Highway Act was passed in 1940s, they were approaching 50 years of the first round of highway payments. Okay, first round. And those payments were failing. Okay. And when they were failing and they said, you know what, I put in 2 feet of pavement, I can't afford it now. I cannot go back and put another 2 feet. Like I know that I understand the material better. That's when federal government gave around $50 million of research to develop something called Superpave, which was $5 million for binder and $45 million for asphalt mixtures. And then also concrete came in as well, right? So what they said is that we need to design this smarter. And what was happening is this. The earlier payments were very much focused on hot temperatures, rutting, not on cold temperatures. Why? Why is always industry always going for high temperature distresses and not cold temperature distresses? Anybody want to guess? Online here.
Most of the network is dealing where temperature is very low. And in the colder regions, the transport is or the facilities are not that much damaged.
Okay, so that's one of the things. So one of the reasons here was that the cold temperatures you don't have that much roadway, and high temperatures you have a larger network of people, a lot of people traveling. So one of the things that is happening is that rutting happens in the first 5 years of the life, right? So rutting is going to happen. It's going to happen in 4 5 years. So if you have just built the pavement and rutting happens in 2 3 years, people are going to notice, right? Oh, abhi paisa kharcha hai. So like what happened, right? Koi to paisa kha gaya, right? So people, everybody was very worried about rutting because they'll remember, oh, abhi to payment repair kiya tha. So everybody, rutting is a tremendous political problem. It's not a technical problem. So that's number one. Second, cracking takes 10 to 12 years to develop. People forget, right? 10 to 12 years, people will not remember when they were constructed. Does that make sense? So also, when it becomes 10 to 12 years, too many things have happened in the life of the pavement, like weathers have changed, traffic has changed, environment has changed. So to predict 10, 12 years out is very challenging. Does that make sense? So the problem, every year that goes by, you try to solve that problem becomes exponentially complex, if that makes sense, right? Because I'm looking ahead, right? I'm predicting ahead, right? And so that's why in the initial industry, if I can keep the problem away for 7 years, 8 years, I'm fine. You know what I mean? I'm going to be good. So that's why they wanted to move. They wanted to see that if they can get beyond. Now let's move. I want to spend time on this slide. Can you guys see this? Everybody can see this? Okay. All right. This is what I do in my class, and this is like an entire table of contents of my entire course, and I'll explain it in detail. I hope everybody online can hear me. So this is what happened in the 1920s and 1930s, right? So I'm going to give us a brief overview. If I was building a design, and let me take can everybody online hear me?
Yes.
Okay, great. So let me take you back for a second, right? And let's say I want to design a pavement for a certain condition, right? What will I do? I hope people can see this. I will take the soil, right? Right? Simple, right? I don't know much about pavements. It's a brand new field, correct? Simple. Remember, the goal is what? To protect the natural soil, right? Let's keep this fundamental. So I know what the modulus of this number is, right? I know the modulus, the soil of this, right? And now what I do is I take this. I have to design this thickness and determine what this property is, what thickness I have to put, what property I have to put, right, to protect the natural soil. That's my goal. Let's come with very simple fundamentals. That's my goal, that I want to protect the natural soil. So what I will do, not knowing anything, right? My goal will be like, okay, I've been given a job, right, to protect the natural soil. I know there are going to be, I just put a number, 1,000 trucks going, right, I'm going to use pounds. I'm so used to pounds, right? So let's look at 100,000 trucks of 54,000 pounds, right? Approximately, right? Give or take. That's the traffic I'm dealing with. A very simple problem, right? Okay. So what I have to do is I will have to, not knowing anything, what I will do is I will get a material closest to me, because I'm here to make some money, right? I will take some material and I will get that soil, I'll build it in my backyard with E2, right? And I will try this H1, I will try this material which is the easily available. Can everybody see that at the back in the online? That?
Yes.
Check it on the board.
So what I will do is, now I do H1, E1, and E2, right? Okay. Now, what my next step would be? How do I know when this will last this? What do I have to do? Remember, I'm here to make some money. I got the easily available material, low cost material, H1 and E1. But what is my next step? What do I need to do? I have to take these trucks and ride over them. Very simple, right? Very simple. So I will take those trucks of 54,000 pounds. Very simple. I'm just giving a thought experiment here, right? And I will run over them, correct? And now it will, after 54,000 trucks, let's say this whole thing has become like this. All right? Fair enough? Because I did not, so I know that this rutted and this rutted, right? My question here is very simple. Is that good or bad? Pavement can't scream at you that it is bubbling, right? You have to tell it that this is failed. How do you decide that? Anybody online? How do you decide that it failed? So this could be, I don't know, I'll just give a number, 2 inches, 3 inches, 4 inches, 5 inches. What is bad? Anybody want to guess online?
It is being transferred to the soil.
Correct. Right, so both of this is transferred to the soil, right? I'm just giving one example. Let's say if I said this after 1,000 trucks was 1 inch, right? Say I did the same experiment, let's say that number was 5 inches. What would I consider fine? Is my question. Pavement is not screaming at you that I'm hurting. You have to tell it that you are failed. How will you determine that? Anybody online? Anybody here?
Serviceability, that means the jerks that is being experienced. And that's one of the that means
What is the criteria? The criteria is safety. Safety of the driver is the criteria that determines is 1 inch okay or 5 inch okay. So this is where you take the concepts of pavements, right? And now how I am helping the traveling public, right? I am helping the traveling public, the taxpayers who's going on to go from A to B. I don't care how you do it. You get me from A to B safely, correct? So now 1 inch and 5 inches there. Which one, what criteria of rutting will I say, oh, this is considered fail? It is safety related. Anybody online, anybody here want to guess? What number, what criteria will define, oh, this number is fail? So in US, this is 1 inch or 3/4 inch. How they must have come up with this number? Any guesses? Any guesses online? What happens when you have 1 inch of rut? What happens during this time of the year? Suspension. No, it's a roadway. There's support there. But what is happening during this time of the year? I'm giving you hints here. Online, anybody still there? You have water holding up.
Raining.
You have water holding up. You have hydroplaning. You have vehicle losing contact with the tire. You have a safety problem. So the entire rut criteria depends on safety. So you have to identify first, what is my goal? I am designing this, right? So if you go to a doctor, what is my goal? I should be able to do this after the visit, right? That goal has to be identified. So you have to identify the goal that 1,000 trucks, 54,000 pounds, if I try, 1 inch of rutting should not happen. If I do that, that's what my client wants. I have done my job. So that framework has to be defined for me to do pavement design. If you understand, I'm giving you a broad, high-level discussion. Is that making sense? Anybody online? Any questions? Can they hear me? Yes. Okay, great. Can I move on? Right. So I did that, and then this became 5 inches. Right? What will I do? I become a little smarter. Right? Okay. I cannot take the cheapest material. I take a little stronger material. And now I can develop based on my experience. Now remember, when I do this, I will be smart before I do a next round. Hopefully I'm a little smarter that I will do some kind of testing of this material and not select something weaker. Right? Does that make sense? Oh, and now I want to make money, but I have to give my client 1 inch after so much. Right? That's how you develop design cables. Right? 1 inch I started, I designed different materials, and now I have next one, I tried another material and I gave 4 inches, certain number, I'm just doing a number 500. I'm sorry, I'm going to still work with PSI because if I think in that terms. So next it's 5,000 PSI, pounds per square inch, right? Does that make sense? Very soft. And let's say this kind of gives you less than 1 inch of running. I may not get in one shot. I have done a couple of iterations. With so just for one condition, I have developed a design chart. Are you with me so far? Now, that's what you do is if I develop these design charts, many of them, okay? So I did it for condition, this soil, right? 5,000 PSI, this trucks, right? In the future, if I want to design something for 5,000 PSI and these trucks, I don't have to go through everything. I've developed from experience. Does that make sense? Now, is that purely non-mechanistic? No, it is mechanistic because you make the material stronger, right? It may seem like, oh, I did not use any mechanics knowledge. No, you did because you are out there to make the material stronger, but it is embedded. It is embedded in the design, if that makes sense. Everybody with me so far? Okay. So that when you develop these different, so if I go here and right here, I take the input environment, subgrade, traffic, right? Now I take the trial section, that means just how I started, right? Now I have a database, I just give you one example, but I did it. Somebody else in some other country, other part of the state did it. Somebody did somewhere else. Everybody did this. Everybody did so far. And now I have a database of all these properties, all this traffic, all this data. And now I have come up with, okay, I want to do it in Srinagar. I want to construct this at E2 equal to 5,000 PSI. And my traffic is 20,000 trucks at, let's say, 120,000 pounds. Let's say. Okay. Now this is my new problem. Right? Does that make sense? Now I have taken all this data that is collected. Right? Now you will have a couple of questions in your mind. My existing data set doesn't have so many trucks, doesn't have so many roads. Let's say. If it does, good for you. You have minimized the risk, you can interpret. If that makes sense to you. So that is what it is doing. You take the environment, you get the trial section, you go straight through and you get statistical correlation to field data. That means I have all this existing field data from past experience, correct? And now you take that and see from the past experience, and now I can get it. However, what happens is that the moment I go outside that data set, I start putting factors of safety. That means I have, let's say none of my test is from Srinagar. So now I have Srinagar as a unique climate. Now I'm going to be safe. I'll apply a factor of safety. So whatever thickness I get from some other country, let's say Dehradun, I will apply a multiplier factor of 10%, multiplier factor of 20%. What I have done, I have absorbed the risk and made the design. That's exactly what Astro-93 is. That it just takes all this data set, and anytime you're not within that, it starts applying factor of safety. That's why the Astro-93 is a very conservative design, because sometimes you are not, it's very expensive to do this, and I'm going to explain some of that next week. Questions for me? Anybody online has any questions? So right here, right now here, you have to evaluate correlations when we move field data. That means every time, if I have more field data like this, more robust my analysis will be. Right? So I always go to New Jersey and say, you have payments being constructed every year. Why don't you do this analysis? Right? They say we would love to, but it costs money. Right? Somebody has to go out and collect payment data, collect traffic data, and so on and so forth. So we suggest to them that you develop your own database and learn from the designs. So every state has to do that, has to take that information and kind of add to the database. But you have to evaluate your correlations. And one more thing here, you have to compare with your payment failure. Remember, I gave you the example of 1 inch, right? You have to give a criteria. 1 inch is failure. 10% of cracking means my tires will burst, right? I will have a smooth ride, right? I will have an unsafe ride, that kind of thing. So you have to develop the criteria, you compare with the criteria, and you see if it's passed or failed, and you start following. That's your empirical design. and some part of my class will touch on every piece of this puzzle when we do the empirical design. That makes sense. So they were only, US only did one in Ottawa, one in Chicago, like literally maybe 20 sections. And they used the ability to analyze and develop the Ashton 93 for the entire world. Right? Just by 20, 30 sections, they could extrapolate. Does that make sense? And everybody used Ashton 93. Questions for me? Can I ask any questions there, please? All good. Next one. So that's one design as well. Now we are going to go to the mechanistic empirical design. Well, let me skip a little bit. Let me go to complete mechanistic design first. Let's say completely mechanistic design. Again, I'm trying to protect the natural soil. You have E of subgrade. Right? My goal is to get as many layers as possible. Let's say I don't want to use any field data whatsoever. What information would I need that if I put in all of this, I will be able to hit my criteria? I'll give you an example, right? Once again, it has to last profit for the next 20 years, whatever is coming. Okay. Environment is changing. It means I need to have environment data, temperature, water, everything. Okay. And I need to have multi-use data. Let me explain this very systematically. Let's say today, right now, let's say it's what 12:30, let's assume, right? So at 12:30 p.m., this particular roadway, right, has temperature of 30 Celsius and a certain precipitation. All right. And at that instant, a certain load is expected. Okay, 50,000 pounds of truck is coming at that location at this time. Right. Got it? Now, what mechanistic means is that if I can predict at that instant, due to this temperature, this rain, this load at 12:30, that means I can take temperature data, rainfall data, look at the impact of temperature and rain on all the properties, and then determine that at that instant, my deflection at the top is going to be 0.0001 millimeter. Fair enough? Just one term. Just one term. Can everybody understand what I'm saying here? Everybody online understand what I'm saying? If I can manage to predict this, that means I have, remember, what missing piece is this? I have to take the rain temperature data for, I've just taken 2-layer system for simplicity. There could be multiple layers, right? So I have to find my E1, I have to do a lot of tests of the subgrade and the top layer at different temperature conditions, different moisture conditions, right? So I will have to do a lot of tests and get a matrix of E versus temperature, all right? Say, right? And E versus moisture, all right? All of this has to be done in the lab. Do you understand what I'm saying? Okay, now, that's not enough. That is not enough. Because this is up in the rain. That means what seepage happens on the subgrade is another problem. That's another node that needs to be modeled too. Okay, let's say we did that. We magically did that for a second, right? So at that instance, that temperature of 30 Celsius and moisture, I came here, that moisture, and I got my E value. Right? Fair enough, but that combination of, so remember, this is E of temperature at a certain moisture level, this is E of moisture at a certain temperature. There's only one. Right? Everybody with me so far? So now I have predicted deflection of 0.0001 mm. Next minute, another truck came, 20,000 pounds. Next 30 seconds, another truck came. Let's assume for simplicity that temperature changed. Got it? Temperature change for simplicity, right? It just rained heavily, right? That cloud burst you guys see, right? And then that you saw the moisture content went up, it dropped, my deflection went up to 0.005 millimeters that instant. I have to do it for the next 20 years. Not 20 years past, next 20 years. Not possible. Impossible, right? How to predict? How to predict what? That's the uncertainty. It's not doing it for today. But if I magically do that, right? Then after 20 years, right? After 20 years, I will get 0.9, just make it simple, 0.99 inches or whatever, right? I have now been less than 1 inches. I just passed my learning criteria. This pavement is okay if I can magically do that. Therefore, we will never, ever be able to do mechanistically this. People in the audience and online and here have to understand, we are trying to achieve that. As much as possible as we get better in this testing, we get better at predicting, right? But this is the uncertainty. Rainfall, temperature is a big uncertainty, right? We cannot predict that. Populations change, things happen, right? This is a fully mechanistic course. What I explained before was completely empirical and statistical, but remember, mechanistic is embedded. So there's a way in between is a mechanistic empirical design. That is the goal of this class, is to give you that. So you come halfway through, but at some point, let me just give you an example. I start to drop the, I cannot predict the temperature. I cannot predict all of that. Everybody understand that? And now, with realistic data, let's say I predicted that my rutting is 0.7 inches, let's say. Right? Realistically, I drop certain things. Now, the chances of you exactly matching that roadway is impossible. Not possible, all right? Does that make sense? Because you cannot predict. What I have to do is have a test section that has gone through these conditions. Okay? In not 20 years, let's say 2 years. Going with me so far? And actually see what the field performance is. So I can somewhat by mechanics, somewhat. I will have an error. But after I have to do the actual field section, actually construct this, and after 2 years, I might have rutting of 0.5 inches. Let's say, I don't know. That means that my entire design has to be shifted from 0.7 to 0.5. My entire design chart has to be shifted and I have to match reality. That's the empirical statistic portion. I will repeat, I went mechanistic how much ever I can go. Right? I will just assume the traffic is going to be so. I will assume that the temperature is not going to change. Or what? Right? For 6 months it's going to remain the same, other 6 months. I can only do so much. So I did all that approximation, the best I could do, and I got 0.7 inches. Fair enough. That's what the real technology right now is doing. That I have only so much power I have going to them. But I will never match the reality. So some test sections have to be done to give a reality check for this. So when my students start predicting this, I tell them stop right there. There's only so much fun you can have on the software. You know what I mean? You can plug anything in the software and it will give you a number. But the reality is this, right? So many top scientists tell me, oh, there are so many lab tests. Which one is the best one? And you look out the window. That is the best one. The reality on the ground is the best one. Nothing else can replace it. Everything is a representation, right? So, and a student get a shock because they do so many tests in the lab. They think they're solving the world's problem, and sometimes they get a reality check that they are just a small representation of reality, right? So then I have to change. If I develop entire design for rutting based on this, I have to drop everything by certain percentage. Does that make sense? So if I made this 0.35 for simplicity math, that means I have to drop everything by half. Does that make sense? So my entire design will be. So NJDOT does it. Every state does this every 5 years. So Uttarakhand should be doing this, right? Every 5 years, gather the data, do the mechanistic empirical design, and do a you can't do this every year. You have to give it some time. But you do a rehash after 5 years. Oh, I did these payments. I get the rutting. I know the properties. Where are we? Where is the gap? Right? And there'll be some outliers. Right? There's somewhere something that those are lessons learned. That some characterization can not be gap. That's mechanistic empirical. That's what that is. So let's look at this. So right here, environment and subgrade, right? I pick a trial section. I develop a payment model. Mechanistic, elastic model, viscoelastic model, viscoplastic model. I calculate stresses and strain. Now I correlate stresses and strain to field area. That's what they did in national. And you go through the same. So now you have added a few more steps compared to the previous one, where there were just a broad range of field sections and I picked one from them. Does that make sense? Here you're doing a little more mechanistic. You have to do, and now how sophisticated I want to be with that. Whether it is linear elastic, non-linear elastic, viscoelastic. The more fancy you make it, this will get closer to this. More fancy your analysis is going to be, more fancy your testing is going to be. You have to know the truth is here. Truth is not here. People feel, academia specifically, feel the truth is here. Because they did all of this. Because they did all of this. No. The truth is this, right? This is what the taxpayers pay for, right? I want my rutting to be less. I want my rutting to be less. So that's a mechanistic empirical, and then you have to look at that, whether it is okay or not. You have to do the same criteria. That's it. Questions? This was the gist of the thing. I always set this stage up as I go through every slide, and then this comes back again and again. But I'm touching on everything: traffic, environment, payment modeling, stresses and strains. But now hopefully the audience will see where this fits in, why I am doing certain things. Because if this is inaccurate, everything ahead is inaccurate. Right? If I can't predict traffic right, doesn't matter, right? If I can't predict subgrade right, I'm in trouble. Right? So everything input has to be accurate, otherwise output is going to be garbage. Right? But again, people like, oh, input costs money, you have to invest. Right? It is investments. People are like, oh, if I invest here, then I will not have failed roads more and more. You are saving money in towns. Questions for me? You want to ask questions?
So you may ask me why in picture for complete online.
Yeah, any questions? These are the important copies of mechanistic empirical design. So right here, this is now will make more sense to you. This slide, right here. Experienced empirical after road test. That's the first road test that were done in Maryland, Illinois to develop those data sets that I explained to you. Then there were statistical models, then performance models, then mechanical empirical. That's what I just explained. You have to look at stresses and strain and deformation and then correlate to field performance that I explained. And then finally, purely mechanistic. That is not possible because we are not in the past. If it was in the past, if I were to take this particular roadway in 2005, 25, sorry, and I say it was constructed in 2005, now you can do an academic exercise, right? Take a roadway constructed in 2005, right? Now I know all the temperature data, right? But it'll be an academic exercise because it's not designed to. Now I can do an effort of, but what about material data? Material is old, right? It's not brand new, so there are a lot of complications there. Right here, evolution of pavement design. 1920s to 1930s was CBR method. CBR is California bearing ratio. That is a test done to evaluate the strength of the substrate. It's a very easy test. It compares with crushed stone and it gives you that. Next, if you keep going 30, 40, 50, right there, Maryland created the first road test. And it's very fascinating. Hopefully I get a chance to explain. Like when you look at those ages, like we look at the brilliance of those engineers to look at that time it cost $1 million, which maybe is so much more money now. With that finite amount of money, they had to develop a design that the entire world is using. So that amount of ingenuity that went in there. And then you have the Astro Road test, 1960s, then the 70s was the asphalt shell design. Why was oil company very involved in the design of pavements? Anybody want to guess online or here?
They are producing bitumen and they are doing a good research of bitumen.
Yeah, they're producing bitumen. Their product is bitumen. It's a completely business decision. All the best research labs are by oil companies, not out of the goodness of the heart, I hate to say it, but it was a business and a strategic decision. So they did very good for science in the pavements field because they saw that if I can design bitumen pavements, it's going to help sell the product. That is absolutely correct. And then finally, MEPG, Mechanistic Empirical Pavement Design Guide. That is the one I just discussed in the specific screen. That was developed by Arizona State University by itself. Right here, actual practice, current practice empirical, that's the Astro 93, which India is using, most of the world is using. Even not the entire US is using that way. State of practice is a little bit moved to the right towards mechanistic empirical. US is right here, state of the art. It is really moving very quickly to mechanistic empirical. But a lot of concerns exist because how to characterize the data. And finally, purely mechanistic, which I had to give you an example of what that means, we will never be able to get right. So that is that. All right. The Astro Road test are limited by scope of the test performed, and this was done. The first test was developed in 1972, right? And one climate in Ottawa, Illinois, right? Tube durations, traffic was maximum 2 million axle loads. Okay. And it was 1950s vehicles, material and construction, and new construction. So you can imagine the limitation of $1 million. They had just this to work, right? And does anybody know what ESIL is? Equivalent single axle load? I'll explain. And this is what happened. The left side, you can see the road test was done by less than 2 million pieces. So the entire roadway 93 is based on the purple data set. Now we are what? 1993 here, 35 years out. We are way high. Not only that, the traffic is increased. We all know that, every part of the world. But most importantly, the tire pressures of the trucks are getting heavier and heavier all across the world. Why? Any guesses why? Why are trucks getting heavier? What has changed in the tire industry that allows them to take heavier loads? Anybody online? Want to try? Huh? Dual? Tubeless. Radial tires. Yeah, steel tires. They have started putting steel, right, in the tires, right? The steel tires. So you have steel tires in there that can take a lot more pressure. right? So it gives you that rigidity to the tire that has allowed the pavement, to the truck people to load them heavily. None of it was designed for, right? And then right here, you can see current designs are at greater than 100. Right, so you can do projection A, projection B, projection C by applying factor of safety. You can see that at projection B, my pavement thickness is going to be very thick, right? Or I can go projection A and so on and so forth. So that led to the development of mechanistic empirical design that we have outlived the ASHTO 93 test sections. We need to do something more different, and that's what led to that. The pretty simple things. Tensile strain, I want to prevent cracking under the top layer, tensile strain, and epsilon compression, I want to prevent the rutting. Rutting in the subgrade has to be protected. Right? What they thought was that I know very little about the climate in the future. If I can have top layer removed and replaced after 10 years, I have a success story. I just know, I only know finite things 10 years from now, right? But if I have done a poor job and I have to remove the entire pavement, I have really messed up. So a million to 2 million became a $20 million project. That's a problem. Does that make sense? So everybody is looking at, I cannot have bottom up failure from the subway. All right, let's look at this. Some tests, some interactive exercise. If anybody want to do online, want to speak up, and I will do that. Which one is which one? 1, 2, and 3 interactive exercise. Anybody online, or anybody want to just indulge me since it's there? One is with B because you are looking at 50 data sets, right, for a given amount of conditions. And if you don't have your new design there, you apply factor of safety. Mechanistic is purely scientific. If I can predict everything in the future, I can get everything by the minute, great. And then the third one, I have to get something. What is the accurate approach to predict axle retardation from beyond roadways? Increase in traffic gets a proportional increase in thickness. Required significantly more accurate. Which one do you think? That's coming to the previous graph, right? If I'm extrapolating from that narrow thinking, right? So if you do it proportionally, like okay, that's a risk you have to take, which we don't know, right? If I increase, if my traffic goes 5 times, does my thickness really goes 5 times? Right? We don't know, right? So that's a cost you will absorb if that's not the case. So you have to really do an honest analysis to get that. That's what led to the development of MEP, mechanistic empirical design. So thickness requirements vary with different traffic levels. So it's not proportional. There's no such thing. Before I go there, any questions? Anything about on? Yeah, check here online. Yes.
Is it possible in future we can stick to mechanistic, purely mechanistic?
It's not, the reason why it's not possible is because of the uncertainty about the environment and the water, right? And traffic, right? So it's purely different design. For analysis, yes. If I took 20 years back, I can be an academic exercise and I can learn from it. Like if I took 20, 30 sections in this area 20 years back, do the analysis, get the weather data, as long as I have material properties also characterized. There's a lot of cost, upfront cost to do that. Does that make sense?
Input requires a significant cost plus the variability and uncertainties even significant.
Like I just give you a simple example. Yeah.
Properties are also very much
unpredictable, right? As it changes. And one more thing is that divisions don't talk to each other. This is the reality. Soil department doesn't talk to payments people, traffic people. Everybody is a different division. So, but payments is one cohesive unit, right? So if all the family members are talking differently, you never talk cohesively. And like for me, I got a project in 2006, 2006 to 2008 to do a mechanistic design for New Jersey DOT. So what I had to do was take 20 years old data that I told you and predict. It took me 2 years to get data only. I had to send my students to the geotech department. Oh, 20 साल का data मेरे पास नहीं है. So we have to look at hard copy, right? Core data, right? And then I went to pavement design. All hard copies. My students were there, took pictures and got that. But they were dying to do analysis. I said, no, you will put garbage data in the program. I will not allow you to do that. So I took them 2 years to get raw data, and then they put it, and that was just a 6-week exercise. Once you get the data, and you will still have to make assumptions, believe me. But at least I know I have minimized the risk, right? I have made a genuine effort to get the closest right answer, and then I made, okay, in this area, subgrade of New Jersey is so much. Okay, I make an assumption, right? But at least I'm not taking the average of entire US. Does that make sense? So I was minimizing the risk, and then I calibrated. So that is a big concern. Now things are changing. Any other questions? Great question. Anybody questions from online? If you guys are still logged in and listening. Yeah, if you guys are still logged in and listening, please feel free to ask any question. I'm going to address a quick question. Yeah, easel equivalent single axle load. Does anybody know about that? It's 18,000 pounds. It is a standard metric of design. Does anybody know online why that number? Anybody knows why that number? Online? I'm trying to say anything. No. It was at that load in 1960s when the tires busted. At 18,000 pounds, when you put 18,000 pounds on that tire, that was the golden standard of the load. Now 18,000 is nothing. That's where the word easel came, equivalent single axle load came, because that was the capacity of the tire at that time. So just to give you a couple of tidbits when students ask me, that's where it came, and I'm going to explain them. So, any other questions about anything? Any curiosity questions from your or online?
Now with this advanced AI tools, like although we have some data, like the one that you were saying that we would put 2 years of data. After that, did you students or they did some predictive modeling of that sort?
We did.
So that that entire wide range varieties, the uncertainties can be considered.
Absolutely, we did. We did that and developed calibration factors for tracking. Yes, that's exactly what the purpose. And that's why I was afraid, because I was giving predictive qualities to a payment when I don't have a good handle of the current situation. But that's what we developed for New Jersey DOT. But the complexity is this: to take the rainfall and the environment, right? That's happening today, right? It rained in the morning, sunny now, let's say. What is the impact of that on the soil? That is only payments business, right? I don't care what is raining outside or what is sunny outside. That's not payments business, right? But there's what is happening to the payment and all the layers. That modeling is extremely complex, right? You need to put sensors. So Rutgers University from New Jersey put in sensors of water and temperature in all the layers for 2 years in different parts of New Jersey. So when they had rainfall data, they had sensor to look at, okay, for that soil structure, if it is rainfall of 100 millimeters, what is happening to the pavement saturation? I can take that pavement saturation and model it there. There's a whole another level of step that is very important. When we start looking at it, it becomes very complex parts. So anytime you're not willing to invest in that, you start to make the layer thicker and thicker and thicker if you don't want to invest, right? Oh, I don't understand this. Increase half an inch, increase 2 inches. You're paying the price anyways.